Good afternoon, everybody. Welcome to sunny Thursday afternoon at Chem 170 with your host, me, Dr. White. Hi. All right, important things. Let's go to D2L. Everybody see D2L on your screen? Thumbs up, people. Thank you, Jimmy. All right, and thank you, Hannah. All right, a week from today, 6/30/22, I will be giving test number 2. You'll be downloading the password protected PDF file from the assignment area at D2L. That will be available this Wednesday, coming Wednesday afternoon. At about 5 o'clock, or maybe even a little earlier, I will send out an email with the password for test number 2 PDF file. You'll have until Friday, 11 a.m. to finish test number 2, upload your test number 2 answers to the assignment area of D2L. In other words, just like you did test 1. Should take you about 40-45 minutes to finish this, but take up an hour and a half, and don't include then the hour and a half time it takes you to scan it or take a picture and upload it. The hour and a half is just working on the test, getting your answers. Now, test number 2 has 9 pages, 10 problems. Some of the problems are multiple part A, B, C, and D. However, I have never and never will give a multiple choice question in this course. Now, it will cover alcohols, thiols, and ethers, ethylene oxide reactions, and aldehydes and ketones, which I should finish today, well in advance of test number 2. Now, if we look at test number 2, we have general knowledge, 11 points, nomenclature, 34, and reactions, which are now more important, I've spent more time on, 60 points. Added up, 105, so there's 5 bonus points. Now, general knowledge, I'll talk about, well, we've talked about nomenclature. There are 2 types of questions. Here's the molecule, give the IUPAC name. And the other type of nomenclature question is, here's the name, both common and IUPAC, draw the structure. And finally, reactions. All but 3 of the problems on reactions will deal with give the organic product or products or the following. But 3, I think it's 3, will be give the starting materials, what I call synthesis. I don't do more than that because that would be cruel, unusual punishment. At least as of today, the Supreme Court has outlawed that. Can't do that, students. But anyways, that's test number 2. And how do you study for it? Do the practice problems. And then if you need to, watch my videos on YouTube or look at your notes. But the best way is do the practice problems. And this will not be an open note test. On next Tuesday, I'll do my world famous review. I got to rewrite it because the one I have is in cursive and some of you can't read cursive. That's my weekend job, to rewrite my test number 2 review and probably knock out test number 3 so you can read it. And on that Thursday, we'll still have our regular Zoom meeting and we'll still have our lab. Any questions on test number 2? I guess not. All right, before we move on, I have to ask, did anybody happen to go in a gas station and you see the sign that says this gasoline contains up to 10% ethanol? Do you think, wow, the gasoline contains ethanol and alcohol? Did anybody happen to pick up a bottle of rubbing alcohol and see it contains isopropyl alcohol, which is an alcohol? Or, thank you, Jimmy, Or if you happen to have nail polish on, you want to get it off and you use nail polish remover. Did you look at the bottle of nail polish remover and see it's got acetone in that bottle? And that's a ketone. So gasoline has ethanol, alcohol, rubbing alcohol, stuff you put on your skin, I guess, and rub. But anyways, rubbing alcohol is water and isopropyl alcohol, which is an alcohol, and acetone is a nail polish remover, and it's a ketone. Now, when I ask on a test, give the name of an alcohol, ketone, or aldehyde you use in your daily life that's in a product, give the name of the product, name the functional group. Would I ask that? Might. And you just had 3 answers I gave you. All right, before we get back to ketones, you know something? I think you people need a pick-me-up. So it's time to do something fun. And what's that fun thing? It's time to play that fun game. What's that fun game? And that fun game is circle and name the functional group or groups in the following, 2 points each. And let's have some fun. And there you go. 4 nice fun molecules where all I'm asking not give the IUPAC name, to circle and name the functional groups in each molecule. 2 points each. Your turn. Have fun. It is. It's a lot of fun. And when you're done, give me a thumbs up. Let's see, let's try that. We got a small group today, an intimate group of people interested in chemistry, organic chemistry, I hope. All right, I think everybody's done, but I'll give you another 30 seconds. All right, let's do this. Now, how do you find a functional group? You look for what's different. What's not a carbon or hydrogen or carbon-carbon single bond, that's going to be a functional group. But for these chapters, don't give it away. Look for oxygen. Oh, look, we've got one right here. And what do we have? And this you don't have to do, but I will. This is what? An aldehyde. This you would have to do. And it's an aldehyde, and that's what you got here. Now let's go to B. Ooh, another oxygen. And it's got a carbon here, double bonded carbons here and here. And what is this? It's a ketone. Therefore, that's a ketone. And you write, circle it and say, write ketone. Now let's look at C. Ooh, what's different? Nope, not that. That's a methyl group. It's a group, but it's not a functional group. Ooh, oxygen, hydrogen, and a carbon. And what is that? An alcohol. And now if we go to D, look for what's different. Ooh, an oxygen here to this carbon, carbons here and here. This is, and it so happens the R and R prime are connected in a ring. This right here is a ketone. Anything else? Oh, wait. Oxygen with a hydrogen on a carbon. This part you don't have to, this you do. And that's an alcohol. Am I done? Oh no, another oxygen, double bond to carbon with hydrogen carbons. And what do we call that? An aldehyde. Aldehyde. And that's how you play that fun game. Circle and name the functional group or groups, 2 points each. I hope you enjoyed it and had a fun time. I did. Now, on yesterday, Wednesday, I started talking about these reactions, and I went through, if you take an aldehyde or ketone, and this could be H and a carbon there, you form a hemi-acetal or hemi-ketal, and you react it with acid and an alcohol. I also showed you yesterday, and good news, we're going to go through these again on Monday, because these are difficult at first for students. So next Monday, this one, the previous one, this one, and the next two, which I'm going to talk about, we will go through on Monday again. Now here, we have 2 molecules or moles of an alcohol, and we get an acetal. This can be hydrogen if it's an aldehyde, carbons if it's a ketone, same thing here. And we make an acetal or ketal. And these, as I said, are the two reactions. Did I just tell you who's one of the greatest of all organic chemists? Mother Nature. And Mother Nature uses these to make starches and carbohydrates and sugars. Now, once you have it, and I think this is where I left off, and I might have done one, but let's go back. And I'm going to rewrite it on my whiteboard. And that's reversing of the hemi-acetal, hemi-ketal, or you could also call it acid hydrolysis, because you're reacting something with water and acid. And as I asked yesterday, where you are right now, where can you find that fast acid and water? And the answer is your stomach. So let's take a look at this. And sometimes, as you see above the arrow, I'll put the water first and the H plus second. This means acid catalyst. And hopefully all know H2O means water. Well, what happens? Well, look for what's different. Ooh, this is unusual. Only happens in two places I know of in all organic chemistry. A carbon with two oxygens, listen carefully, single bonded to that carbon, not double, single. And on this oxygen, we have carbons. This oxygen, we have hydrogens. And attached to that same carbon, we could have carbons, but no, this example, we have hydrogens. And then over here, well, how did that become red? That's strange. It's not Friday the 13th, is it? Anyways, we have, whoops. We have an R group, and I'll call that R double prime. And now, when you add acid and water to this is a hemi-acetal or hemi-ketal, you'll get back the aldehyde or the ketone you would have used to make this compound, plus the alcohol you would have used to make that compound right here. And here, what's our prime? Hydrogen. What's our double prime? Methyl. What's the carbons on the oxygen up here? R. So, and I should have put two question marks. The first is carbonyl. What's attached to it? Our primer hydrogen. Our double prime is methyl. And that's one product. And the other product comes from the R group to make this alcohol. Listen carefully. The carbon with the oxygen is the carbon this hydroxyl group will be on. The carbon with this oxygen here will be the carbon, the hydroxyl. Well, in this case, there's only two carbons. So, and that's what you get. And it's time to let you try one. And here's one for you to try. Hint, look above it. And when you're done, give me a thumbs up. Or let's see if I can convince anybody. Turn on your webcam and smile so I know you're done. Shucks, didn't convince anybody. Remember, when you're done, give me a thumbs up. Or if they have it, which they don't, you give me a thumbs down. Or they have hitchhiking. Hitchhike, that's illegal. Don't do that. Plus, it's dangerous. If you're finished early, please be patient. I try and give everybody time to finish. And like I said in the previous two reactions, in this one, I'll never give synthesis problems for this reaction. All right, let's move on. Let's do it. Now, here's the hint how to get these types of reactions. If you ever see a carbon atom with not one, but two oxygens single bonded, not double, single, they're always going to give the same product. And the reaction is right up here. Keep your eye on the carbon with the two oxygens, becomes this carbon. Then what's our prime? Methyl, right here. What's our double prime? Or it's actually right here, ethyl. So carbonyl, carbon double bond oxygen, our prime methyl, our double prime ethyl. Next, I have my alcohol. And where do we get this R group? From the carbons on the oxygen right here. And this one is only one, but the carbon this oxygen is bonded to will be the carbon this hydrox group is on. Well, there's only one carbon. And there you go. All right. Let's try another one. I think you could use it. And I'll help you out. I'm helping you out too much. Keep your eye on the carbon with two oxygens, becomes this carbonyl. And you get this alcohol. So what I should have done here is this. And there you go. Your turn. What would be the product, organic product or products for the following reaction? Like I said, these are harder. And I'll give you a hint. There's the hint. All right, let's do this. Now, if we look at this molecule, what's different? And here, this chapter, look for oxygens. One here, it's the same carbon. Notice one is OH, one is oxygen with carbons, OR. And here, you got carbons here and here and here. One of these I can call R prime, the other I can call R double prime. And what happens? Well, this carbon right here in red becomes this carbon. Well, actually not like that. We have the ring, which is attached to this carbon. And we have a carbon-oxygen double bond, in this case, a ketone. Next, where do we get this R group? From here. And here we have two carbons. The end carbon has the hydroxyl group, and this is how you would do that. So that's how that reaction goes. Now let's move on. Unless you have questions, remember, there's no such thing as a dumb question in my class, my world. All right. And this reaction here, and next one, I have it labeled reversing the acetal-ketal reaction. I could also put acid hydrolysis of an acetal or ketal. That's how your stomach starts breaking down starches. So if you had anything with starch in it for lunch, this is going on in your stomach, not to scare you. And here, similar to the previous one, you have a carbon with two oxygens bonded to it. And each oxygen has an R group on it. The R prime could have been hydrogen. And we have carbons here, acid and water. The carbon with the two oxygens is this carbon. And R prime and R double prime is, this is what you get. And you don't have to put the two there because I never asked you to balance it. But this R group comes from this one right here. And if we look at this molecule and react it with acid and water, H plus and water, the question is, what's the product or products of the following? Let's look at this. What's different? What's not carbon? What's not? Ooh, an oxygen, another oxygen, and they're single bonded to the same carbon. Then I have carbons here and carbons there. I'll call that R prime, and this R double prime, which is the same as this. And when you add acid and water, look at this carbon. The carbon with two oxygens becomes carbonyl. And what's directly bonded to it carbon-wise, or hydrogen carbon, will still be bonded to it. Now, if we look also, we have this and this, and that becomes this alcohol. Now, you don't have to, but let's see how small I can make it because I don't want to do it. You can put a 2 there, but you don't have to. So if we look at it up here, and by the way, R prime could have been hydrogen, we have R prime, R double prime, and both of these are R. So R, look at the carbon with the two oxygens, that will become this carbon. What's attached to it, R prime methyl. What's attached here, R prime methyl. Then we have these carbons on the oxygen, which become the carbons of the alcohol. If you want to, you could put a 2 there. You don't have to. That's why I make it small and in quotes. And that's how you do this reaction. And let's have you have a try at it. And on a test, I would have done this. And there you go. What are those 2 question marks? What products you get when you react that molecule with acid water, H plus water? Your turn. And remember, this reaction, I will never put on test or final as a synthesis problem. By the way, this one gives the same products as the last reaction, just if you balance it, it's different. But I don't ever ask you to balance it. For those who came in late, I talked about a week from today will be test number 2. I talked about the announcement in Blackboard that you also should have received as an email. like I said, these are tough ones. This one, the previous three. I'll go through it again on Monday. That way you'll do good on test number 2, which is a good thing. I think I get more iron in my diet. All right, let's get moving forward. If I look at this, what's different? Oxygen, second oxygen to the same carbon, they're single bonded. And on this carbon, I have a hydrogen. And I have carbons, I can call this R prime and this R double prime. And then on that carbon, I have 2 single bonded oxygens, and there are groups on the oxygen. I call that R, that R. And you have, in this case, acetal. And the first question mark, or doesn't matter what order you do, you have the carbon with 2 oxygens becomes this type of carbon, carbonyl, and the R prime, which is hydrogen, and the R double prime is methyl, and there you go. And now you need the alcohol here, and notice R is 3 carbons with a hydroxyl group, and the N carbon here, in both cases, bond to the oxygen. Therefore, the N carbon here is the product you get. And if you wanted to, you could put a 2 there. You don't have to. And that's how you do it. Oh, let's do one more. And there's the one more for you to try. And let me move it so you can see the general reaction. There you go. Give the organic product or products to the following. And if this were on a test, you'd see this and this telling you they're 2 products. And I won't do this on a test, but for you, I'll do the following. Remember, look for what's different. This chapter is oxygen. In fact, all the stuff on test number 2, look for oxygen. All right, since we're right about break time, I'm going to break in. Oh, that was awful. And let's do this. In case you're not finished, I want you to have your break on time. And if we look at this, what's different? Oxygen here, oxygen there, and they're single bonds to the same carbon. And what we have here, each oxygen has carbons. This is our R group. And this carbon here has carbons here, here, here. This one goes here. So we have R prime, could have been hydrogen, it's not, and R double prime, and they're just connect together. Now, when you react this with acid and water, keep your eye on this carbon, becomes the carbonyl. In other words, you go back to what you started to make this. And on this carbon, we have our prime or hydrogen, because you don't break carbon-carbon single bonds. And we have our double prime. Now, on the oxygens, you have an R group, and they become alcohols. And the carbon with the oxygen here is the carbon with the hydroxy group there. So let's do this. This carbon right here is this carbon, which means I have that ketone. Then my R group is methyl. So I have this alcohol, and that's what you get. Oh, I went a whole 2 minutes over. Let's take a break and come back at 2:57. I'll see you in 5 minutes. Take a break. let's get going. All right, let's move on. Like I said, I'll go through these reactions again, those that we just did on Monday. All right, now you can go sigh of relief, some easier reactions. Now, the following reaction is called the Grignard reaction, and it's named after one of the greatest of all organic chemists, the French organic chemist, Victor Grignard. And here's a picture. Does everybody see the Wikipedia for Victor Francisco, or however, Augusta Victor Grignard, Dr. Grignard? And he won a Nobel Prize for his Grignard reagent and using that reagent in what's called the Grignard reaction, named after him. And he died in, wow, young age, 1935. And he was French, obviously. You can see where he taught and also where he got his degrees from. And the Grignard reagent is a fun reaction to do. So let's look at it. What is the Grignard reagent? How do you make it? You take an alkyl halide, and I don't have it here, but I'll do it now. And react it with magnesium metal. You do this in a solvent like diethyl ether or other ethers, and you form the Grignard reagent, which is this right here. Now, let's go to my whiteboard because there's something I need to tell you about this. That's not my whiteboard. That is. All right, let's look at and here you have an alkyl halide, and the carbon with the halogen will be bonded to magnesium, and that's bonded to the halogen. I'm about to sneeze. Hold on. The snow slowed. Whoa, excuse me. All right, now this is wrong. That's wrong. The carbon, our group, is bonded to the magnesium, and the halogen is bonded to the magnesium. Not this order. It's wrong. So please don't do that. So let's have some fun. By the way, the magnesium is bonded to the carbon and R that had the halogen. And let's look at the following reaction. The question is, give the organic product or product. And if we look at this, we say, oh, what's different? Halogen on a carbon. Oh, that's RX. Wait a second, magnesium metal. And you react it, and what do you get? Remember, X can be chlorine, bromine, or iodine. And what you get is RMGX. Now, do you break carbon-carbon single bonds? No. So I have 4 carbons here. That's my R group. I better end up with 4 carbons. And which carbon has the halogen? This one. And that's the one that's going to be bonded to the magnesium, and the magnesium will be the iodide. This counts as one bond. So I know there are 4 bonds to carbon. And I'm done. And that's fun. It's easy. And this reagent allows you to do some amazing things. So the carbon with the halogen will now be bonded to the magnesium. Magnesium is bonded to the halogen. Your turn. Give the organic product or products for the following. It's actually one. I put more than one question mark, or I put question marks. Just on the test, I will, when that occurs. If you're done early, please be patient. I try and allow everybody to finish. If you're finished, do the poll, or turn on your webcam so I can see you're done. All right, I think everybody's done. Let's get to work. We look at this, we look what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Ooh, a halogen on a carbon, that's an alkyl halide, where X can be chlorine, which it is, bromine, or iodine. Ooh, magnesium metal. And what do you get? You get the Grignard reagent. By the way, Victor Grignard is one of my heroes of organic chemistry. What's our R group? This. The carbon with the halogen is the carbon this magnesium would bond to. Do you break carbon-carbon single bonds? No. So I have 4. I better end up with 4. The N carbon has the halogen, which means it'll have magnesium chloride, and that counts as 1 bond. So I know how to put the hydrogens in. And I did. And that's the Grignard. Oh, let's have one more, do one more thing. As I mentioned, on test 2, there'll be not 1, but 3 or 4. I forgot. I'll have to go back and count. Synthesis problems. What do you react with magnesium to make this compound? Your turn. All right, I think everybody's done. So I'm going to get to work. Now, how do you do synthesis? Well, you look at the reactant and say what's different, what's not carbon, what's not. Ooh, magnesium chloride on a carbon with other carbons. I'm going to call this R, and I can do this, where X equals chlorine. In our case, could have been bromine, or it could have been iodine. And it's a Grignard reagent, named in honor of the discoverer, Victor Grignard. And what do I react with magnesium to make the Grignard? Alkyl halide. And the carbon with the magnesium chloride was the carbon with the halogen. What's my halogen? Chlorine. I have 4 carbons like this. I better start with 4 carbons. And on this carbon right here, I have the magnesium, so I should have the chlorine. and I'm done. And that's how you make the Grignard reagent. And that's how you synthesize the specific one. Now, one of the questions you should have is, what are you getting all excited about a Grignard reagent? What do you do with it? This is what you do with it. You do the Grignard reaction. And in all of organic chemistry, there's only a handful of reactions where you can make a carbon-carbon single bond. Very rare, very special, very good. And the Grignard reaction allows you to do that. So let's take a look at it. Now, I have to introduce you to some, before we talk about this, let's talk about a convention. I haven't used that, but I will in the future. Let's say you take A, and first you react it with B. And now, second step, you react it with C, and you make D. Now, I could have written it like this. Not like that, come on, like this. A and B make something, you react it with C, and you make D. But organic chemists like doing this. Now here, the number one means the first step, what you react A with. And then after you react it with B, a second step, you react it with C. Well, in this case, first step, we react the ketone or aldehyde with the Grignard reagent. Second step, we add acid and water to get an alcohol. And let me go now to my whiteboard because it will seem easier. Start with an aldehyde or ketone. First step, Grignard. R triple prime is this different, can be different from R prime or R double prime. Second step, acid and water. Now, I'm going to show you something you don't have to write down. First of all, as I mentioned earlier, the carbonyl carbon is slightly positive. That little delta here means slightly, and the oxygen is slightly negative. Now, when you react that with the Grignard, think of a Grignard, think, it's not actually, is R minus, sort of like that, MgX plus. If you got a negative charge on carbon, it's looking for a positive charge right there. And here's what happens. First step, this happens. And this attacks that and opens it up to this. And here we did that special thing. We made that carbon-carbon single bond with my Grignard. Now, this is a conjugate base of an alcohol. And when I add acid and water, I'll remove this and make an alcohol. And that's the Grignard reagent. This is called the mechanism, which I really don't have time to do, but this is so exciting I had to. So let's take a look at this. Now, as a special gift to you, don't tell anybody I'm being nice, okay? This Grignard reaction, not making the reagent, but the reaction, this general reaction up here, I will never put a synthesis problem on a test or a final dealing with this reaction. You'll have to know how to give the product or products, but not the starting materials for this reaction. I can, but I don't think it's fair to you at this level course. So the question is, what's the product or products, organic products of this reaction? If we look right here, what's different? Ooh, carbon double bond to oxygen. On that carbon, we have R group, R prime, and another group of carbons, one, R double prime. We have a ketone. What do we have that's different here? Ooh, carbon on magnesium chloride. The Grignard reagent. Second step, acid and water. And remember, this attacks that, and then it gets a proton, and you make an alcohol. And that's what you get. So if I look here, this is our prime, this is our double prime, and this is our triple prime. Keep your eye on the carbonyl carbon. That's where the fun is. What's attached to it, R prime. Could have been a hydrogen, R double prime, OH, and not with an oxygen, directly bonds to this carbon here is the R group from my Grignard, which I just lost my train of thought. It pulled out of the station without me. We have our R triple prime, and that's the methyl group. And notice here, I've made a carbon-carbon single bond, very special, very rare. And that's how you do it. And here's one for you. At the bottom, you'll see a molecule, and you'll take 2 steps. And what do you get? Your turn. Again, I will never, ever, ever put a synthesis problem on test or final with this reaction. It's fun, but not at this level. Not fair. And remember, if you have any questions, always feel free to ask me, email me, or come to my office hour. And if you can't come to my office hour and it's really something you need help with, email me and we'll see if we can set up a Zoom meeting. Nice thing about Zoom is I don't have to drive to ECC and you don't have to drive to ECC. It is really nice because if we were face to face, the only time I have office hours when I'm at campus, that's Monday and Wednesday right after class. All right, I think everybody's done. Let's move forward. And the question is, what's the product or products? And in this case, what's different here? Ooh, oxygen double bond to carbon with a hydrogen, could have been R prime, it's hydrogen, and carbon's here. And this is a carbonyl, carbon double bond to oxygen aldehyde, could have been a ketone. Then what are we reacting at here? First step, carbon, magnesium chloride, it's a Grignard reagent. And second step, acid plus water. Don't forget that X can be chlorine, bromine, or iodine. Most of my work I did with chlorine. But anyways, this attacks that. Organic chemists are violent. What's bonded to this carbon are prime or hydrogen. Our double prime is still there. You open that up to a alcohol, OH on a carbon's alcohol, and then you do that very special rare thing. You make a carbon-carbon single bond between the Grignard and the carbonyl carbon, the carbon double bond to oxygen. So this is my R prime, this is my R double prime, and here is my R triple prime. So I'm gonna do my, what was my carbonyl carbon? Hydrogen attached to it was R double prime, 2 carbons, and an alcohol. And what's my R triple prime? 2 carbons bonded to this carbon. And there you go. And oops, forgot something. That's how you do a Grignard. Oh, these are fun. I got to have you do another one so I could do it too. And there you go. What would be the organic product or products for the following reaction? All right, let's get moving. And if I look at this molecule that I'm starting with, what's different? Ooh, oxygen, double bond to carbon, carbon's here. It's a ketone, cyclic. Could have been an aldehyde, but it's not. And what's different here? Carbon, ooh, magnesium bromide. It's a Grignard reagent. And X can be chlorine, bromine, which in our case it is, or iodine. Next, second step, acid and water. That's what H plus and H2O are. And keep your eye on the carbonyl carbon. I'm going to write that first. What's attached to it, R prime or hydrogen. Our double prime is still there. This opens up to an alcohol, OH, and then I have R triple prime. So the ring here with the methyl group are my R prime and R double prime. They're just connect together. So I'm going to redraw that. And I did, because you don't break carbon-carbon single bonds. Here's this carbon, that's this carbon, that's this carbon, that's now that carbon. This will have a OH on it, alcohol. Then it will be bonded to my Grignard reagent carbons right here. And that's two carbons. And there you go. You've made a carbon-carbon single bond. Very special, very rare. All right, let's move on. To the next one, and that's hydrogenation of a carbonyl compound. And meaning a ketone or aldehyde, if R prime is hydrogen, it's an aldehyde. Now, this is a double bond, and that's a pi bond and a sigma bond, except instead of being carbon-carbon, it's carbon-oxygen. If I add H2 in a catalyst, and a catalyst can be nickel, platinum, or palladium, you break the pi bond, and each atom of the double bond, in this case carbon-oxygen, gets a hydrogen. And this is a way of making alcohols from ketones. So let's take a look at this. If I take this molecule, react it with hydrogen nickel, what happens? Well, what do we have here? Ooh, oxygen double bond to carbon with hydrogen, but it could have been R prime or in this our case, hydrogen, and carbons here, R double prime. And then I have hydrogen and a catalyst. Whoops, I've been pretty good about that. What's he talking about? Well, right here, let me use the eraser. I wrote in cursive instead of printing, catalyst. And that's nickel, platinum, or palladium. And now what happens? You break the pi bond, and each atom of the double bond gets a hydrogen. What was attached to this carbon is still attached. I think I got ahead of my, hold on one second. And this should be our triple prime. And so here's my R prime, our double prime. Here's my carbonyl. Put that, single bond to oxygen. Each one gets a hydrogen, break the pi bond. Let's attach that carbon, hydrogen, and methyl is still. And it's probably the most expensive way I know of making ethanol. And now I've got to let you try this. And it's your turn to try it. What would be the organic product or product? Let's see, let me try something here. No, hold on. I'll help you out underneath. And there you go. And now you do it for that specific molecule. Should I try when you're done? Give me a thumbs up. Does that still work for you people? Let's see. Don't forget to vote. In fact, tomorrow morning, I'll mail in vote for the primary coming up next week. Don't forget to vote in that. Right, men and women have died, so you can vote. So please vote if you're registered. You can register, I believe, the day of the election at your polling place. All right, let's do this. What do we have that's different? Ooh, an oxygen, double bond to carbon. Carbons here and here, a ketone. It could have been hydrogens here, an aldehyde. Hydrogen and a catalyst. You break the pi bond, and each atom of the double bond, carbon oxygen, gets a hydrogen. So I have this, I break the pi bond, and my R prime and R double prime are still on this carbon. And I'm done. But this is a reaction I can do a synthesis problem. What do you react with hydrogen and a catalyst to make that molecule? All right, I'm going to have to jump in here because it's almost time for our break. If we look at this molecule, what's different? Oxygen with a hydrogen and a carbon. Now I could write it like this. And then R prime on this carbon, or hydrogen, and R double prime. In this case, one of these hydrogens is my R prime, and this is my R double prime. And what do we react with hydrogen and a catalyst? Oops, I almost did it again. Where did I hear somewhere on a program? It's all right, come on. Uh-oh. Well, it looks like we're going to go a little into the break. Sorry about this. That's not what I wanted. Okay. All right, back to work. Sorry about that. Now, if we look at this, what do we react with hydrogen and a catalyst? where the catalyst can be nickel, platinum, or palladium? And the answer is a ketone or aldehyde. And notice we end up with 3 carbons. We better start with 3 carbons. 1, 2, 3. The carbon with the hydroxyl group is the carbon double bond to oxygen. And on that carbon, our prime is the hydrogen. And our double prime are these 2 carbons. And that's how you do it. And with that, it's time for our break. Ooh, wow, sorry, I went really over. Let's say, come back, oh, what the heck. Come back at 3:55 and we'll continue on. I'll see you in about 5.5 minutes. I don't know if I, what time did I tell you? Oh, I'm a minute. Oh, I'm late. I'm sorry. Let's get back to work. One more reaction, and then we'll have our lab. As a special treat to you, I'll let you out a little early today. Yep, a special treat. All right, let's get back to my whiteboard. And there's a problem with hydrogenation. What's the problem? What I'm going to write down, don't write down. Well, if you want to, I won't stop you. Say you want to, it's called reduce this, make this into an alcohol. Well, you say, oh, that's an aldehyde. And I know the reaction is an aldehyde or ketone reacting with hydrogen and a catalyst. Well, do this, the reaction I just talked about. You break the pi bond between the oxygen carbon, and each atom of the double bond gets a hydrogen. But I do not want to lose the double bond between carbons. However, if I were to do this reaction, guess what? You learned for test one, a double bond reacting with hydrogen and a catalyst like nickel, you'll break the pi bond and you'll get that. Well, in reality, if you try this reaction right here, and these real scientific terms, you get a mess. First of all, you could get this happening where the double bond is not affected. And you'll make this alcohol. But this also could be reduced, hydrogenated, and also the aldehyde could be. I'll draw it since I move this over here. And this, I don't want to lose double bond. I did. There's a third one where just the double bond is hydrogenated to the aldehyde is not. So you get a real bad mess. Well, it turns out this was a serious problem. There's a great organic chemist from University of Purdue, Dr. H.C. Brown, who figured out a new reagent to allow you to keep the double bond, but reduce hydrogen, like hydrogenating, but a different reaction, a ketone or aldehyde to an alcohol. And he won the Nobel Prize for that. This was at the end of World War II. I should mention, in World War II, especially World War II, because certain supplies were cut off from the Americans and the Allies, fighting the Germans and Japanese, that the field of organic chemistry became very active to supply those chemicals or products that were now cut off, make them synthetically, artificially, and H.C. Brown was part of that effort. Now, what is his reaction? And the reaction he came up with, first of all, new reagent, Li, lithium, Al, aluminum, 4 hydrogens. This is called lithium aluminum hydride. And it reacts like it's a Grignard instead of R triple prime. It's a H minus, like, not real, but you think of that. And therefore, you first step, lithium aluminum hydride, second step, acid and water. That could be a slash too. And you break the pi bond, and just like with hydrogen and catalyst, each atom of the double bond gets a hydrogen. This will not react with carbon-carbon double bonds, but will react with carbon-oxygen bonds. And that's because it's a nucleophilic attack. And now, as you learned earlier, 2 steps. This is the first thing you do. And I've worked with lithium aluminum hydride. It's nice. You don't use it in a plant, it's too expensive, but in a research lab, this is the way to go. And I have done that. And what's the general reaction? Keep your eye on the carbonyl. What's attached to that, R prime or H, and our double prime is still there. You break the pi bond, and each atom gets a hydrogen. This is like hydrogenation, but this will not react with double bonds, carbon-carbon. So if you want to react it, and actually there are places where when you make certain steroids for medicine, you don't want to lose the double bond. So this is my R prime, which is an H, R double prime. Keep the eye on the carbonyl carbon. I do. H is still there. My 2 carbons are still there. And I break the pi bond, and I make this alcohol. And I could have written it, let me move me and you over here. Whoop. I could have also written it and now you see it's an alcohol. And that's the beauty of lithium aluminum hydride, using it. And that's why H.C. Brown got a Nobel Prize, because it was a great advancement. All right, your turn. And I don't know if I have time today, probably don't. I'll come back to this on Monday, but you can do a synthesis with this one too. But your turn. Get to work. Oh, that wasn't polite. Bad, Dr. White. Your turn. Have fun. That's better. And while you're working on that, let me open up something. And don't forget to vote in the poll. And I have to apologize. We're moving at a good clip today. And if it was a little difficult for you, feel free later tonight. I'll have posted today's Zoom meeting on my YouTube channel for Chem 170. So you can always go back and look at it and maybe watch it in slow motion. And for those who finish early, please be patient. Try and give everybody time to finish up. All right, let's do this. And if we look at this, we say, what's different? What's not carbon? What's not? Ooh, an oxygen. That's double bond to carbon. Carbonyl. Carbon's here. I'll call that R prime. Carbon's here. R double prime. It's a ketone. Now, it could have been an aldehyde. And what am I reacting with? Well, first of all, lithium, aluminum, and the H4 is called hydride. I'll never ask that on test. And second step, H plus is acid and water. And what happens with this reagent? It's like hydrogenation. You break the pi bond, and each carbon of the that. I always do this when I teach this. Each atom of the double bond gets a hydrogen. So it's attached to that carbon, R prime or hydrogen, or R double prime is still there. Break the bond. Each atom of the double bond, carbon oxygen double bond, gets a hydrogen. So keep your eye on this carbon, which is this carbon, which becomes this carbon. What's attached to it? R prime methyl. R double prime, 3 carbons. And then I break the pi bond, and each atom of the double bond gets a hydrogen. I know there are 4 bonds to carbon, so I can put in my hydrogens. And I'm done. All right. That's how you do it. It's lab time. It's time. Let's have some fun with the lab. And today's lab deals with alcohols. And let's take a look at it. And Today's lab deals with alcohols. And let me remind you, what is an alcohol? I haven't asked all day. I've been pretty good about it, but I better ask now. Thumbs up, people. Do you see the alcohol lab on your screen? Give me a thumb. Thank you, Jimmy. All right, now, if we're face to face, you do this, and I'd remind you never in an organic lab light any matches or anything like that. And I'd also remind you, and I'd show you in the lab where the various wastes from this experiment go, because this lab, none of them go down the sink. All right, first thing, you're going to determine the solubility of alcohols. And is the alcohol soluble in water? Well, I told you earlier that alcohols, there's a slight negative charge due to the electronegativity of the oxygen, hydrogen, slight positive charge on the hydrogen. And water has the same thing. And here we have this slight attraction, which is called the hydrogen bond. And that helps make certain alcohols soluble in water. But if R has too many carbons, then this is overcome, and this doesn't help make it soluble. Well, how do you know if something's soluble or not? Well, you mix two things together, shake them up, and let them sit. If you get the same throughout, we call that homogeneous, it's soluble. If it separates into two layers, it's not soluble. Well, in today's lab, if we were face to face, you'd put about, in small test tubes, about a third of a test tube with DI water. DI means deionized. We have it in our lab. There are special filters that take the ions out of the water. When you drink water, there are ions in there. It's not pure H2O. Then you add a small amount of the alcohol and you mix it. Let's assume this is a test tube. It's not, but assume it is. In the lab, you should never, ever mix it. No, no, no. One, you hold it firmly and go 1, 2, 3, 4. Don't tickle it. Really hit it hard. The other thing, which we have at ECC, we have these what's called Vibro Mixers, and students love them. I like them. And they're a motor with a rubber disc that comes up from the motor. And when you push down, it's actuated, and the motor causes it to vibrate real fast, and it mixes up too. And you put that in a test tube holder, come back in a minute or so later. If it's all the same, it's soluble, homogeneous. If you see two layers, it's heterogeneous, not soluble. And if we look at today's lab, since you're not going to do it at home, here is the different alcohols you would be testing. And ethylene glycol, isopropyl alcohol, tert-butyl alcohol, also known as 2-methyl-2-propanol, 2-hexanol, 1-oxidol. Now, notice in red, please draw the structures for the alcohols in this table below the name of the alcohol. So right here you have space. Here it's a little crowded. If you need space, put it out here in the margin. And you have 2-hexanol and 1-octanol. And if you notice, some are soluble and some are not. Now, next one, which were there, odors of alcohol. Are there any trends based on size, shape, whatever, how it smells? So you would have these alcohols, we have little squares of paper towels, put a little on and smell it. And if you are there, here's what students say it smells like. All right, now the last part is called oxidation of alcohols. And you learn, take a primary, secondary alcohol, you oxidize it, you'll get a ketone or aldehyde. Tertiary don't react. Now in this lab, and I'm going to show you the exact equation, you'll be using acidic potassium dichromate. And you'll put about 10 drops of the alcohol in the test tube, about 10 drops of the reagent, acidic potassium dichromate, mix it like I just showed you, or use the Vibro Mixer. I like that Vibro Mixer. And then let it sit for a little while and observe. Now, here's what I have to teach you. Primary alcohol plus sodium, or am I using potassium dichromate? Which one do I have in the lab here? Potassium. Both work identical. And if you react it with this is potassium dichromate. And remember, you've seen me write on top of an arrow, bracket O, close bracket. Well, this is one of the reagents you'd use to do this. And if you have a primary alcohol, you will oxidize this to an aldehyde. Now, this is a red, orange color, depending on reddish orange, depending on the concentration Dr. Daly makes this solution. Now, when this gets oxidized, this gets reduced to a chromium +3 species. I'm not going to write it out. And depending on the concentration, this is either blue, blue-green, almost a turquoise, or green. So if you see a color change from reddish orange to blue, blue-green, or green, you know you had a primary alcohol. Now, if you take a secondary alcohol, and oxidize it with potassium dichromate, which you can. And again, it's red, orange, and now you'll get a ketone plus the chromium +3 complex. And again, it's these colors, blue, blue-green, and or green. However, if you have a tertiary alcohol, and reacted, oxidize it with potassium dichromate, guess what? No reaction. And how do you tell that? Well, this is red, orange, reddish orange. If you have a tertiary alcohol and mix it with potassium dichromate solution and you don't see a color change, you know you have a tertiary alcohol. And this part of the lab, it's fun to look because the colors are beautiful. We'd mix it and notice ethylene glycol, blue, blue, green. Isopropyl alcohol, blue, blue, green. Ooh, 2-methyl, 2-propanol, orange, red. 2-hexanol, blue, blue, green. And 1-octanol, blue, blue, green. And you'll be asked questions about that. Now, the final part I do is a demonstration because most students don't know how to handle sodium metal, and it's quite hazardous if you don't. I've worked with it a lot, so I can do it. And let's look at the final reaction for the slab. Now, if you have an alcohol, any alcohol, and watch closely, this is one of the rare times I'll balance equation, because students get upset when I don't, and I don't need upset. And you react it with sodium metal. And what happens? This reacts to make this compound plus hydrogen gas given off as bubbles. Now, this is called an alkoxide. And alkoxides are very basic. They're stronger than sodium and potassium hydroxide, much stronger. And in case you forgot, pH scale, below 7, it's acidic, a solution or whatever you're measuring. At 7, it's neutral. And above 7, it's basic, meaning a base is present. Well, if I'm telling you the truth and we react alcohol with sodium metal, the products, if you measure the pH, should be very basic. And how do we measure that? pH paper. Give me a thumbs up if you've ever used pH paper. I guess you haven't. Thank you, Jimmy. Thank you, Hannah. pH paper changes color, different colors, and we have the ones we use. There's a little chart, and you match the colors. So let's look at today's lab. In today's lab, what I would do is in a beaker, I put some isopropyl alcohol and some water. Next, I measure the pH of that. Next, I take the same alcohol, 2-propanol, isopropyl alcohol, and react it with sodium and take some of that and put it in water. Remember, pH is always measured in an aqueous solution, and measure the pH. Actually, what I do is stick the pH paper in there and show it to the students, and I ask for volunteers. I give them points for anybody who volunteers. I say, what's the pH? And they get it right. And if we're doing it in the lab, the 2-propanol, isopropanol, or propyl alcohol, water has a pH of 7. The reaction product of 2-propanol and sodium, which I just showed you the reaction, has a pH of 13. In case you didn't remember, that means it went up, it became very basic. Oh, I'm not lying to you. That's a good thing. And that's today's lab. And don't forget to answer the questions at the end. And with that, I'll remind you, don't forget, hand in the lab that's due today. Once in a while, one of your colleagues, I actually found it first when I was turning on today's lab. Sometimes I'll make a mistake, and the interface they have, you can make a mistake. And also, since I'm used to doing a lab due the next week, not 2 days later or a couple days later, if I make a mistake and when the date it should be done, like today should be next Tuesday, let me know and I can correct it. And I did this morning. And with that, I'm going to let you out a couple minutes early. Shh, don't tell me. Actually, I don't have to be here the whole time. It's an internet course, but I try and do it like a face-to-face course. And with that, don't forget, a week from today is test number 2. Monday, I have one more reaction And on next Tuesday, I'll do my world famous review for the next test, test number 2. Over the weekend, I got to rewrite it so it's not in cursive, which some students can't read. And I'll post it Saturday or Sunday, the review, but I'll go through that on Tuesday. And probably next Tuesday or Wednesday, we'll do the problem set for ketones and aldehydes. How do you study for test number 2? Do the problem sets. With that, have a great rest of the day, great weekend, or Friday and weekend. Don't forget, Friday night is the next Stanley Cup playoff game. Last night was so exciting game to watch. I did. I'm a hockey fan. And with that, I'll say, Gang gesund. Goodbye. I'll see you next Monday.